All right, so I'm on mute, right? Could you hear me?
Yes, loud and clear.
Okay, good. Yeah, thank you. Yeah, because my internet sometimes is not very stable, so I turned off video and just show the slides. Okay, and I think I have this one here. Okay, at least a point. Okay, great. Okay, thank you, Mike, for introduction, and also want to really thank organizers to keep this virtual meeting instead of totally cancel that. So today I would like to talk about how are we going to design ligands and to tune the binding kinetics, and also talk about free energy too. And before I start, just an advertisement. The group is recruiting a postdoc to work on the project I'm going to talk about. So our goals, the same as many people in this workshop, this is the $1 million questions. How can we predict binding affinity accurate enough that we can use a modeling tool to design ligands? And here I expand this a little bit to also design ligand to tune the binding kinetics. And this is also a $1 million question because not just $1 million question, save $1 million because organic synthesis is very expensive. I think it's a tradition from the Gilson group. We're all very fascinated in understanding binding kinetics, binding mechanisms and driving forces. Like if you have a kinase system with a different loop, with different population, and then those are different. You may have a gating effect, you may have different processes, slower or faster. That could help you to design the ligand too. So I'm not going to talk about the details, but let's focus on affinity. So the first thing when we think about binding free energy, typically the first question we ask is, do we have a co-crystal structure with a ligand? If the answer is yes, and then we feel happier because that's a little bit easier start. So like we already heard many good talk, a great talk about free energy perturbation, also the previous talk using a faster method and docking. And so we typically focus a lot on crystal structure bond state, or the conformations closer to the crystal structure bond state. So they offer a lot of information, which is true. Okay. And typically this is enough if you can consider conformation or waters there. But then I also question, think about this. What does it mean bond state? So it's not we decide the bond state, but it's an experimental method that tells you what the bond state is. So for example, think about SPR method. For this method, as long as the ligand stay with the protein, stay longer enough that the signal is triggered and the machine sense that the ligand is with the protein, it considers it as a bond state. So, and then the experimental data, so that's what you can show. Different method may have slightly different delta G, and also those bond state affect or tell the binding kinetics. So here, what we are thinking about is not just the crystal structure bond state or conformations closer to that, but we also want to investigate a little bit more about other transient bond state that is not trivial to see when we have a crystal structure. So this is a link to binding kinetics. So binding kinetics could be important or can be less important, but from the great introduction from a previous talk like Daria or Alex, they give us information or background about binding kinetics can be important. But for years, we don't really pay too much attention on that because typically tighter binder also stays longer. You see the correlation, they are more efficient. Okay. But it's not always true. So this is what we usually do. So this is an exception. Like it's not just a very few, but like 20–30% of the system, you may see sometimes it's problematic to take just a simple binding affinity to rank this or to link that with a functional efficacy. Because in order to design a ligand to make it better, we are looking for a good correlation of some property, biochemical property we can obtain experimentally or computationally, and then link that to good functional efficacy. So this one doesn't have good correlation if we use affinity. And so biochemists may play with the different values they have. And here, if instead of using affinity, if they took a drug residence time, which is 1 over dissociation rate constant, and then plot this with a functional efficacy, you see better correlation. So there's a lot of reasons we still not fully understood why this may link better to efficacy and pharmacokinetics. But the idea is here is instead of consider only crystal structure bound state, we also consider the bound state. And so think that the here is the x-axis here is an unbinding corner. Can you imagine any unbinding corner? And y-axis is a free energy profile. And classical view, we focus a lot on crystal structure bound state. This is actually enough, or the bound state closer to the crystal structure conformations. But because the bound state is not only there, so the entire process that the ligand stays there longer enough, that could have an influence to your binding affinity and also largely affect the kinetics. So our idea is, could we predict not just tighter binder, but also longer binder? And maybe we can use those transient bound state and to design our ligand. So say, for example, look at the differences for the mother compound and some compound we can design, and then add something, decorate that, just like we do this, but focus on a bound state, like a free energy perturbation. And then to make the longer and tighter, and then do experiment. So this will give information about binding kinetics, but we do need the free energy and play with the free energy barrier to achieve the goal. So here we use cyclin dependent kinase A with the cyclin C as our model system with different ligands. A set of the ligand, here I show 5 of these, and you can see that they are big enough, like a real drug-like compound, and they are a pretty tight binder, and they have a residence time experimentally. And here it's we consider not only crystal structure bound state or bound state closer to this, but those transient bound states that the ligand is unbinding during unbinding processes. So you can use some other method to investigate this area, and we don't consider much about this unbinding path when it's outside on the surface diffusion, although it's still important. Yeah, but the sampling need to be very thorough. So currently we focus on this and try to predict binding affinity and also their kinetics property. So we use metadynamics to do the unbinding path. Okay. But we do need a free energy profile to tell us what to do the next after we get those conformations. So this is the result. I want to show you how we use the ideas to do the design. So this is the ligand, and it's not the tightest binder. The best binder on this series has this relative free energy 0 here. You can see this ligand has about 2 kilocalories per mole, at least a weaker binder than this one. So it has a binding residence time here. So you can see this is a crystal structure bound state, or the conformations closer to that. So those are some transient state. So we take a look of this and check it carefully, and then decorate the ligand with a hydroxyl group. And the idea is we want to increase the free energy barrier. So by increasing the free energy barrier, we hope that it can make the ligand stays longer in the pocket because it's harder to leave. And sometimes it can also reshape the free energy profile and make the delta G by stronger. So here we predict it's roughly 1 kilocalories per mole stronger, and at least it's kind of a 3 times slower residence time. So we think this is the compound and carry out experiment. So that's the experimental value is indeed it's more than twice longer than the original mother compound, and also it binds tighter for this. So how do we achieve it? So here I'm introducing a new method that we call the binding kinetics tool package, and use this model system. Here we adopt milestone theory to get the free energy profile and also get the approximate residence time. So this is the result that what we can get using the adapted milestone theory is that the x-axis, we put in the milestone index here, but you can imagine that this is basically unbinding path or coordinate, or unbinding pathway, which one you want to tell. And then this is our free energy profile. So the top 3 is tighter binder. So not surprising that their energy landscape is more locked. And for weaker binder, this is pretty typical. They are kind of boring on free energy profile. So different from umbrella sampling, which we tried before using a little bit simpler unbinding coordinate, we do not see this kind of rugged free energy profile. So make it harder to use the free energy barrier to design. So here it's how can we achieve this rugged or a more accurate free energy profile to design. And before we move on, it's this is the validation for our calculation. So the y-axis is from calculation. This is the binding residence time, and this is free energy. So this is experiment. So except the one outlier, it's the trend actually holds very well. So we're confident that the calculation is doing a good job. So use this method for the design. So first, a little bit more about the details for this package. To begin with, we always run a reasonably long classical MD simulations for the crystal structure bound state. So here is we start from this and run MD simulations, and the purpose is to check the binding pocket to see how flexible they are and make sure the system is stable, of course, and then pick up conformations from our classical MD to run metadynamics. So you don't need to run the metadynamics. You can use a different enhanced sampling. And the purpose is just to enhance the conformational search or sampling to allow you see not just conformations here, but it also goes to those transient bound state. And the other thing important that we run so many metadynamics to get a lot of unbinding pathway is because we want to make sure for the systems we have, there's only one unbinding pathway. I mean the direction, which is from here. So from the previous talk, like Daria's talk, you can see the ligand sometimes may go from different unbinding direction. So in this case, each unbinding direction, you may want to take their unbinding pathway to investigate that, because if you do not know which one is the dominant unbinding pathway. So here, life is simpler since we only have one. And then there are two novel things that we have to do to modify in order to let this method work for this complex system. One is the new strategy to assign milestone, and the second one is the new strategy to get the free energy profile, and also get the basically it's constructing a matrix to get the free energy and residence time. So this is from the idea is from milestone theory, but we have to modify them a little bit. Okay. So tell a little bit more about milestone theory. Some people may be familiar with that, but for people who are not super familiar with this, it's the idea is kind of similar to Markov state model, that instead of running a very, very long simulation, continuous simulation to get, say, unbinding residence time or some other kinetics property, we would like to just use a lot of shorter MD simulation. Typically, it's pretty short, okay? And then to construct a matrix like this, we call it transition matrix, okay? This is transition between milestones, and then analyze this matrix, we can get compute the residence time. And we also, from analyzing this matrix and using the equation here, we get the free energy profile, but it's not always that easy. So here, the system I got from Romi's paper. So their lab developed the secret package. That's say this is cyclodextrin and this is a different ligand. So the milestone theory is before you get this matrix, what you can do is you start to manually or whichever you want to assign milestone. Here, each milestone is, you can see a lot of circle here. Imagine this is a sphere, kind of interface sphere of some space or a sphere, which is with a different distance away from the center of mass of this gas or of this host. Sorry. So in this case, you draw a lot of sphere, and each sphere is a milestone. Okay, and then say let's start with one milestone to pick up this purple one here. So then we do run like umbrella sampling or some other method to place a lot of initial conformation along this milestone to start a lot of short MD simulation. So say, for example, take aspirin, use umbrella sampling, place a lot of initial conformation here, and then let it run. Okay. And then once the aspirin reach to the blue milestone, we stop it. Once it moves to the black milestone, we also stop it. So this is the transition to the nearby milestone only. So then we count, okay, 90% inward, 10% outward. So we construct this matrix. So can we do this for our system? Theoretically speaking, yes, maybe. But in reality, if you look at the unbinding trajectory, you can see that manually assign interface or milestone along that will not work. Because if you look at the system, you see the ligand, when it's dissociating, everything is jiggling. I did not turn on sidechain because it's too busy. You see a lot of sidechains in motion, see alpha helix is in motion, some loop is in motion here. So it's very hard or impossible to just use a sphere. So it's not going to work because it simplifies the whole system too much. But you cannot also consider all X, Y, Z since there's too many degrees of freedom to assign milestone. So what do we do? So what we try to do is my graduate student and then a postdoc in my group, Chia-en, had this very small idea. He used the principal component, which is a mathematical way to process this unbinding trajectory. So take the first two PC mode, and you can see the motion. So not just the ligand moves, the protein also moves. So using these two principal component modes as a coordinate and to assign milestone. So basically what you can see that all the jiggling here, you can imagine there's a lot of conformation of frames from this unbinding process. So each frame or each conformation is presented as a dot here in this picture. So this is the closer to the bound state, and this is a little bit outside. So each dot is instead of so many jiggling here, 3 minus 6 degrees of freedom, we reduce that to 2 degrees of freedom. So of course, some of the motion is still neglected, but so far this is one of the easiest way that we can try our best to preserve the motion, but also assign milestone. Okay. So in this case, we still have to manually assign the milestone path and also give the milestone here. And so how well this representation can be for the unbinding. So if I take each one conformation along each milestone, this is the way you see. So combine them together, and it looks like a pretty smooth unbinding. So we use this as our unbinding coordinate. So which is the x-axis you see. So here we have to do one more thing to make this practical for this application. Because previously for exact milestone, they constructed this matrix by running a lot of restraint MD like umbrella sampling, okay, to put the conformation here and you do the termination. But think about this, we have more than 100 milestones. And also this is in PC1, PC2 space. So it's not practical to really run umbrella sampling for each of them. And another advantage we already have is we do have a metadynamics run, have a lot of conformations on this milestone.
Hey,
Okay.
Chang.
So what we do, yes.
It's okay, but you're getting into your Q&A session, just to let you know.
Oh, okay. So I think I have. You let me know, okay? Yeah. So how many minutes I still have?
Well, in principle, 5 minutes.
Oh, okay. Yeah. All right. So I'll finish this in probably 2 or 3 minutes. Okay.
Okay. Thanks.
Yeah. Okay. All right. Sure. All right. So okay. So here is what we were trying to do is instead of running a lot of restraint MD to make the practical for this kind of particular system, it's we actually took those frames from metadynamics. Those are unbinding processes, and then we pick up those conformations and then let it run MD simulations, and then we process this. I'm not going to talk of the details, but we process this and don't need umbrella sampling, don't have early termination, and construct that. So we also double check with some distribution along each milestone. It's kind of okay, right? So, okay, so I'm going to finish this, but the idea here is telling you that we do need some free energy to guide us about how we're going to do the design. So this is one slower ligand. This is a faster ligand. And then we observe what happened, not just in the crystal structure bound state or bound state closer to it, but also transient bound state. So this is a little bit busy picture, but after careful investigation, we noticed that there is a room that we could play and make it a bulky or add a hydroxyl group to enhance or to keep the ligand longer there to increase the residence time. So after consulting with the organic experiment experts, so this is the only ligand affordable for synthesis. Others are too expensive, so a few $1,000s is okay. And then this one, as I just showed you, is after decorating the hydroxyl group, they change the free energy profile a little bit, but the more pronounced is increasing this barrier to make the ligand stays longer, and then also increase the make it stronger a little bit. Okay. So let me finish and conclude. It's I'm introducing this package, and the process here is first. It also encourage you to, if your system it's a kind of looks a little bit funny, I also encourage you to take a closer look to those transient bound state. So you may use a different enhanced sampling method, metadynamics, or like different MD, accelerated MD. Okay, and here it's we are also using the adapter milestone theory to get a free energy profile. So we use this BKIT package to reduce the dimensionality from 3-6 to 2, but still capture natural motions. So your unbinding coordinate, it's a bit more like a last artifact or last artificial. Then we run a lot of short and deep simulations and then construct the free energy profile. So to help us do the design. Okay. So the design, again, it's not just a bound state, but using the transient bound state and the free energy barrier and validated by the experiments. Okay. Finish. So the first, I would like to thank my two former group members, Han and Jie, to finish up this project, and the current postdoc, Jeff, is working very hard to finish this BKIT package. Will be available free to everybody soon. And also group members who work on this CDKA system, and colleagues discussion for milestone theory, enhanced sampling, or organic synthesis, and funding, and everybody here. Okay, thank you very much. Yeah, I finished this.
Thank you, Chia-en. That was great. I think we have time for, there are several questions. I'll just go from the top. There's one from Yun Luo. So she's asked, by introducing an additional barrier along the unbinding pathway, do you see some cases in which the binding process is slowed also?
Could you repeat the question again? So what do you mean the barrier for?
I think the idea is that you're introducing a barrier for unbinding, which makes K off slower, which is what you want to do. Does it also slow down K on?
Yes, so in this case, yeah, so sometimes it's typically issue also slow down K on, but the free energy is, the profile is actually pretty complicated. So in this case, the whole free energy profile also reshape a little bit. So the K on, K off is not directly correlating. So that's why you see this case, the delta G also change. In some cases, we also see that you make you change K on, you change K off, you also change K on, right? And then that's why the end of you don't see any difference in delta G. Yeah. Okay. So we do have this case, not in this system, but for others.
Okay, and there's I think another one from Emilio Galicio. Are the principal component amplitudes mostly related to the ligand degrees of freedom? Do you see interesting couplings with the receptor degrees of freedom?
Yes, it does. It has to. They have to do this coupling or if it does not couple together, you can simply use the center of mass. So the reason we dropped the idea using center of mass, which we did before, is because we need a better way to see the coupling. So the movie was not clear, but you can see when ligand is unbinding, the protein, like the loop, helix, and also some other side chain also move in concert together with the ligand. So this is what you need as a consideration for your milestone or for your unbinding coordinates. Yeah.
Great. There's a couple more questions, but I think we're running out of time. I don't want to keep people late. So maybe you can just answer those on the Q&A session with text. So thank you again.
Yeah, thank you.